Alright, so we are starting our third unit of the 9 weeks as we begin to talk about mechanical energy, and we're working our way through the whole semester of different types of energy that we're focusing on. So I don't know about you, but I had fun today watching you guys do these different methods of walking from one line to another in order to calculate your speed. So just remember that tomorrow we'll be using that information we collected today in order to calculate the speed that you were traveling as you hopped and walked backwards and speed walked, and just had a blast doing that with you guys. So I hope you guys had fun with that, and we're going to apply that tomorrow. So I just want to be sure that we understand what the definition of speed is, because it's something that you experience and you're very familiar with it every day, but sometimes it's hard for us to grasp like the actual definition of something that we're so familiar with. So speed's definition is that it is the change in position of an object per unit of time, for every unit of time. So in other words, how fast an object can move. Speed always has a positive value, and it is non-directional. So that means that you're never going to see a negative number for speed. And it also doesn't have anything to do with going like north or south or southwest. Like, it doesn't have a direction attached to it. So when you see like a speed limit sign, you're not going to see a negative number. You're not going to be told what direction you're going. It's just a number. And during the warm-up today, we talked about what constant speed means, and it means that the speed does not change during a certain time. So hopefully you remember from class we discussed that we can use cruise control in cars to keep cars going at a constant speed, so a person driving doesn't have to keep using the gas pedal themselves, but the car will do that for them. We talked about how I usually do that in the morning, so I don't have to tire myself out even more than I already am. And we'll talk about some more examples of that when we're in class tomorrow. So we do have a formula, and it got a little weird when it got put over into this video format, but the time and the t should be directly under this underline for distance. So it's speed is distance divided by time. Some of you in class got to this point in the lab today where you were dividing the distance you traveled in the hallway by the time it took for you to do that. So when I am traveling 40 miles an hour, and we usually say mph, another way to say that is m/h, that means that I have traveled 40 miles in 1 hour. So if I'm driving along and I know I have an hour left in my trip, I know I'm probably going to go about 40 miles. So in the metric system, we use meters and seconds to make things even more simple. And please remember, we don't use miles. We usually convert things to kilometers if we're dealing with things that are long distances, such as traveling from one city to another. And so remember that the slash we see there is read as the word per. So some examples on your own paper. If a car travels 90 kilometers in 1 hour, the car is traveling at a speed of, and the answer is already written here for the PowerPoint, 90 kilometers per hour, because it's your distance divided by your time. And that we have to pay very close attention to the units that you're given, kilometers and hours, and you just put a little slash in there. So if an ant moves 2 centimeters in 1 second, then we could say the ant's traveling 2 meters per second. And if the sun is 144 billion meters away from the Earth, and it takes 480 seconds or 8 minutes for the sun's light to hit Earth, which is true, then the speed of light is 300 million meters per second. That is super fast. So basically, it's just very simple division. You're dividing the distance by the time to get your number. So if we were to look at graphs that portray the distance traveled and the time it takes to travel, it gives us a really good idea of how fast an object is moving. So if it's moving at a constant speed, it means that we can expect the same increase in distance in a given time. So that means that this line here is going to be a constant slope. You're not going to see any dips or curves or anything. So we just said a few minutes ago that cruise control for a car is an example of an object moving at constant speed. Okay, and if you can think of any others, I want you to brainstorm a little bit about this question. See if you can think of anything else besides what we talked about in class today, and I would like for us to discuss this tomorrow. So try to brainstorm. If you can't think of anything, maybe ask your parents or a brother or sister or somebody that you're around, maybe even some friends on the bus tomorrow morning. But I want to talk about this question a little bit in class as we're finishing up the lab from today. Okay, so when distance does not change, that means an object is stationary. So that basically means it is not moving. So an example of when an object is stationary, let's just put that in terms of a car, because we discussed that earlier with cruise control. So a time that I would be not moving would be like any time I'm at like a stop sign or a stoplight. And then if you want to try to apply this to anything else outside of driving, again, I want to talk about that tomorrow in class as we're wrapping all of this up and moving on into finishing up the lab. So in this graph here, you see that this line here stays level the whole time. The distance does not change, but time is still going. So when it's level like that and it's like flat with the ground, then that tells us that the distance hasn't changed and the object is not moving at all. So we want to know what slope can tell us. And remember, the slope is how steep the line is. Just to remind you from, it looks like it says sleep, from math class, what slope means. So both of these lines here show that each of the objects move the same distance, because the distance is connected right here. And my line is awful, but you get the point. But we see that the yellow line gets here in a faster time than this teal line does. Okay, hopefully you can understand that. So because the yellow line got to that distance faster than the blue one, that means the speed was higher. So a steeper slope means that it moved a larger distance in a certain time. In other words, higher speed. So the higher the slope, the higher speed there is. The lower the slope, the longer it takes to get somewhere. So the slower the object is. Okay, if both of the lines here do have a constant slope, that means that they're both in cruise control, if you want to put it that way. One just has the cruise control set at a higher number than the other one. So it's kind of like me driving to work in the morning. I could be going 60 miles an hour on cruise control, and Mr. Kirschberger could be going 50 miles an hour on cruise control. And that means I'd get there faster, but we're both going a constant speed. So there's something we haven't accounted for when we're traveling in cars or buses or however. We are going at certain speeds, but we also want to take into account where we're headed. That's where velocity comes in. Velocity is the same thing as speed in terms of our formulas that we use, except this time we have to remember this involves a given direction. So this means that velocity could be positive or it could be negative based on where the object is going. Directions could include things like left or right. They could be cardinal directions such as north, south, east, west, and all those combinations. And again, our formula got a little bit messed up, so these bottom things are not centered the way they should be. This should actually, I want to cross that out. The T should be on the other side of the triangle here. So velocity is the change in position over time. So change in position is your distance. You're dividing it by time. It's the same idea as speed. The difference here is that we want to include a direction after the number to say where we're going and not just how fast we're going. So we want to ask ourselves, are the jets flying at a constant velocity? The answer is no, they're not. You might notice they're all going 600 knots, which when flying or when riding a boat, that is the method of measurement. So they're all going the same speed. However, they're not all traveling in the same direction. If they're not going in the same direction, that means they're not at the constant velocity. There are two that are going in the same direction and the same speed, and hopefully you notice after a second, if you look at it, it's kind of like Blue's Clues again. If you circle the two that are going the same velocity, you would choose both A and C because they're both flying in the same direction. B is going the opposite direction, so if we were to compare the two, we could even say that it was a negative 600 knots because it's going on the same line but in the opposite direction. D is just doing his own thing. So this is it for the notes. You do have some practice problems to do for the very last part of these notes. If you feel comfortable using this formula, all you're doing again is distance divided by time. You're welcome to do that by yourself. I'm going to make a second video in a short while after you've had a chance to do it. And if you feel like you need that extra help, please watch that video to help go through all the steps of doing these problems so that you'll have everything filled out for tomorrow and you'll be ready to go with finishing up our lab. Hope you have a good evening, and I'll see you later.